This is quite bright here. My name is Thomas Weible from Flex Optics, co-founder of the company. And we are specialized in optical transceivers, especially when it comes to pluggable modules. And this talk I made because in 2018 people started to think about 400 gigabit technology. And I figured out when I jumped into that part that there are some new technologies coming up, especially when it comes to modulation on the optical line. And that's what I'm going to talk today. My background is mainly I was responsible for the software engineering part within Flex Optics, and now I moved more and more towards to the technology part, especially when it comes to getting transceivers in your network up and running, building applications out there, and that's mainly what I do today. So starting with the technology part, yes, there will be some theory at the beginning to understand the 400 gigabit, because otherwise it's going to be quite tricky. And the easy part is we are talking about a pulse. So we got here a pulse, a pretty simple one, representing 1 bit basically. So this pulse has two events, a low event and a high event, and I think that's something what we know from high school physics. So a digital signal has 2 events representing 1 bit, pretty straightforward. The other thing is when you take such a pulse and you do it on a high-speed manner, or it's a high-speed signal, you might have heard about a term of an eye diagram. I heard quite a lot of network engineers talking about eye diagrams, but when you've asked them, hey, do you really know what it is? The only thing what they tell me is, oh, we want beautiful eyes, and that's basically what we need. But so far, no one understands it exactly, and that's what I want to explain now. So see on up there, we got a sequence of 3 bits basically, 0, 1, 0, going through those 2 event status, low and high. But thinking of 3 bits, they can also, 3 bits with 2 events gives us 2 to the power of 3, gives us in total 8 different states we can achieve, or these bits can achieve. So starting at the top left corner, we got 0, 1, 0, and going down it's like 0, 0, 0, 0, 0, 1, etc., etc. You might see the different shapes here. You might ask yourself, hey, previously Thomas showed there this rectangle shape, and now it's more a sinus. We are talking here about a high-speed signal beyond 10 gigahertz, and the rectangle is no longer a rectangle, so it's more a sinus-shaped curve. Now, how does this come to a combination of an optical eye diagram or an eye diagram? Is when you combine them, and you have to look down there, all those 8 different schemes I showed in the previous slide. When you combine them and you overlay them all together, you get something similar like this shape down there, the one in the blue. And here up there, you actually see a 100 gigabit eye diagram measured with a scope, representing our different states here, and the events of high and low, having 1 bit. And what does make an eye diagram? An eye diagram is the section in the middle, basically, this shape here. So that's the shape we don't want to cross with our signal. So our transmitter shoots out the signal on the fiber, and the receiver, he needs to determine if it's a low event or a high event. But if the signal goes through that shape, or actually it goes a little bit off, the receiver, he can't determine any longer if it's a low or high signal. So then we get bit errors. And that's what you see on your interfaces when you encounter CRC errors. That's what happens when the shape is either too wide, and or if the eye is dodgy or broken, and that's what you really want to avoid. You want to avoid dodgy eyes. This was me trying to play ice hockey, but I wasn't very successful. The next thing, so this, what I showed now or already, was about the current technologies we have on for 10 gigabit or even for 100 gigabit used. Now for the 400 gigabit, a new thing is introduced, and it's done on the modulation. So we do have our rectangle shape again, having 2 states, but now we add 2 intermediate steps in the middle. So we got here the low state, and now we get H3, like highest 3, and we get H1 and H2. So in total, these are 4 events. And the great thing about having 4 events in one pulse is you can represent 2 bits with it. So just with the amount within a single pulse on the same frequency like previously, we can encode or modulate basically double amount of data bits in one single stream. And that's which is done with 4-level pulse amplitude modulation, which looks like this monster here, or that beast. So we still got those 4 events here, low up to H3, and we got now, instead of 1 shape, we got 3 shapes. So what does our transmitter has to do is, for example, if he wants to transmit a 0-1, it goes down there up here, and in the next stage, where it wants to transmit a 1-1, for example, it has to go up here, all the way up and down. And that's the tricky part to modulate it, basically, that the receiver still has the ability to determine on which level are we. Are we here, are we here, are we here, or down there? PAM4 is one of the key drivers now for 400 gigabit, which we will see by the end of the year, but more on the practical approaches I will show later on. So far the theory. Now what about how it will really look like? I mean, we heard a little bit about the theory, but as I said at the beginning, the talk is about transceivers, about pluggable transceivers. So what will we see there? So first I want to do a recap on 100 gigabit, because I think that's quite helpful to understand where we are coming from. And 400 gigabit technology and development is really, really focused on 100 gig, and you will see it later on the upcoming slides, that there were some pretty lessons learned which were made on 400 gigabit, which learned from the 100 gigabit. So opening up a 100 gigabit transceiver, it's straightforward. We have 2 sections there. We got an optical engine and we got a electrical side. So here we got the golden fingers connecting to your host, driving 4 times 25 gigabit, connecting those 25 gigabit to an optical engine doing also 4 times 25 gigabit. Doesn't matter if single mode or multi-mode, we don't care at the moment. Now for 400 gigabit, it will look pretty much similar, but beside the fact we got now 50 gigabit here, same frequency though, it's because we got PAM4. So as I said at the beginning, previously it was an on-off keying representing 1 bit. Now we got PAM4 doing 2 bits with the same frequency. So we just doubled the data rate up to 50 gigabit, although the frequencies stayed the same. And the amount of lanes was increased from 4 lanes up to 8 lanes. So when you do the math, this gives 400 gigabit on the electrical side. This electrical side is connected to the optical engine, and this is at the first stage, and that's really important to know. So the first generation of optical transceivers for 400 gigabit, of pluggable 400 gigabit transceivers will run at 8 times 50 gigabit on the optical side. So in terms of multimode, for example, this will be a SR8, so running 8 lanes, 8 fibers, 850 nanometer with 50 gigabit each, and you need in total 16 fibers because you also have the receiver side. Now, as you can imagine, it was already a hassle for 100 gigabit operating 8 fibers. We have to operate now 16 fibers. There needs to be a little bit more intelligence, and that's in the second generation. So in the second generation, the optical engine goes up to 100 gigabit, and that's the major difference there. So we are driving there an optical engine with 4 times 100 gigabit, still PAM4, but increasing the frequency there. Now, on the electrical side, it stays with 8 times 50 gigabit, and on the transceiver itself, there will be a chip placed, an ASIC, which is called a gearbox. And what does this gearbox do? It's pretty simple. It takes 8 lanes of 50 gigabit, combines it to 4 times 100 gigabit. There's not much to do so. Why is there a gearbox and not just running plain 4 times 100 gigabit on the electrical side? The answer is in money. When you want to produce a PCB providing 100 gigabit, it's going to be really costly, very expensive, because you need different PCB material like Teflon or ceramic, and that's going to be really, really high expensive. So it's even cheaper just placing a chip on there, which does the conversion from 8 lanes to, with a lower data rate, to really short lanes. So this connection is really short, that's really need to be short, to 100 gigabit connections. In terms of form factors, we will see 2 new form factors coming up. So you might be familiar with the QSFP-28 so far. That's the one which we are currently using for 100 gigabit. There have been some predecessors like CFP-X family, like CFP-1, CFP-2, and CFP-4. But in these days, the majority is talking about the QSFP-28 as a pluggable module, as it's easy to produce, cheap, and can support up to 10 kilometers pretty easily, even beyond that in these days. The great thing is about QSFP-DD is it's a further development of the QSFP-28, and the QSFP-DD socket is backward compatible to the QSFP-28. So when you have a switch with a 400 gig port having a QSFP-DD, DD stands for double density, you can plug in a QSFP-28 into that QSFP-DD port. How does this is made? First of all, the physics are pretty much the same. Beside the fact on the golden finger side, so on the golden finger, the connector to your host on a QSFP-28 is 1 row. A QSFP-DD has 2 rows. So the first section is the one which is backwards compatibility to the QSFP-28. And when you plug in a genuine or a pure QSFP-DD 400 gigabit transceiver in a QSFP-DD socket, both connector rows are used to drive those 400 gigabit. And an alternative one is going to be the OSFP down there. The dimensions are pretty much, it's not realistic, but it's more the proportions are pretty much equal to each other. So the OSFP will be a little bit bigger than the QSFP-DD, but it has really one great advantage. It's going to have a integrated heatsink. And why is this important? We will see at the end when we come to the power consumption. Right, I mentioned the dimension, and I think the portion inside the switch is not so interesting for you out there in the field, but I think the portion outside of the switch, that's a critical one. And why do I mention that one? Is we have seen, some of you might have installed a couple of years ago, 6-7 years ago, the first SFP Plus 10 gigabit DWDMs, and they had a huge heatsink at the front, and they were sticking out of the front unit of your router or switch pretty much. And you might ended up having issues closing the front door because you had that big portion of around 30 millimeters of the which sticks out of the front unit of your switch. Plus you got the LC plug of your jumper cable, another 50 millimeters, and then it's fiber optic. You still need a little bit bend radius because otherwise the light doesn't go through. And this will end up with at least 130 millimeters of space in front of your first rack unit to the front door. And if you have less, you either bend the fibers too much or you can't close the door any longer. And the bad news is for 400 gig it won't change. So the longest portion which can stick out is 35 millimeters, and that's defined, or the vendors of the transceivers have agreed on that. So you better have enough space in front of your first rack unit when you design your racks and placing that gear. And that's a critical question because you also need to be aware what is the depth to your second rack unit, and then you need a little bit space also for the AC or DC powering and wiring, and then you might end up with the question, hey, is a 1000 millimeter rack still sufficient, or we just jump on 1200 millimeters, because that's where we are at the critical mass when you do all the math from the front door back to the back door. What will come here on the connection side, that's what I'm going to show next. So 400 gig, it doesn't matter if we're talking about QSFP-DD or OSFP, there is a nice way to do kind of an application, because we are talking, as I said, on the second generation of four times 100 gig single lambda. So each lambda or each connector depends on the fiber is going to be used, and also technology-wise, will drive 100 gigabit. And the great thing is we can connect legacy 100 gigabit gear, which is already in place out there, with either QSFP-28, not the ones you have already installed. So there will be new QSFP-28s coming out doing a single lambda 100 gigabit, and not compared with the current ones doing it on 4 lambdas or on 4 wavelengths. And also the form factors for 100 gigabit will improve. We will see a micro QSFP there, or a really hot candidate is the SFP-DD, because SFP as a form factor was very successful in the past, and I'm pretty sure it will also be quite successful in the future because it's easy to handle and yeah, also easier to produce than other form factors. Right. For sure, what I didn't show now is that you can do a legacy 400 gigabit connection from one end to the other and connecting two transceivers with each other. So that's more a breakout scenario doing 100 gigabit. When it comes to IEEE, and that's a critical part here, so what I have shown previously is mainly on the multi-source agreement, where different manufacturers agreed on how we make the sizing, what kind of form factors we will have. But when it comes to the optical interface, the IEEE plays a major role. And why do I mention that? Because when you look down on the bottom, we got LR4 there. The LR4 is quite long. You will see it on the next slide where the specs are there. But the majority of you might be familiar with LR4 at 100 gigabit was defined with a LAN WDM up to 10 kilometers. And these ones were not introduced yet so far for 100 gigabit. And you might, when you operate your network and connect it to an exchange point, for example, you might have identified that your exchange point only offers you LR4 interfaces doing 100 gigabit. When you look at bigger ones like Lynx or DKIX or AMSIX, for example. And you might question yourself, hey, why don't they offer other things like CWDM4, CLR4? These technologies were introduced also with 100 gigabit, but, and that's the major difference, they were never standardized by IEEE. So the working group which was working on 100 gigabit was the 802.3BA. And now the 400 gigabit working group took that lesson learned and said, okay, we have to standardize not only LR4 technology for single mode up to 10 kilometers, we also have to standardize 2 kilometers, the FR4, and even a parallel single mode technology, DR4 up to 500 meter. You would say, yes, I know that, and we have that already for 100 gigabit for sure. The technology is there, but it was never standardized, and that's the major difference to 400 gigabit. There is now an official standard FR4 and DR4. I also mentioned like FR8 or LR8. It's just the amount of lanes for the first generation, 8 lanes optical side, and LR4 will be, or FR4 will be the second generation with 4 optical lanes. So how do they differ? DR4 is mainly the intention is doing data center interconnects, especially when you look at this one, this type of application. So you have a breakout mode 4 times 100 gigabit up to 500 meters in a parallel single mode way. You might have seen those breakout cables with the MPO plug on the one side and then the LC duplex on the other side. FR4 up to 2 kilometers and with a CWDM wavelength grid, so having a spacing of 20 nanometer between the waves, which is similar to the CWDM4 for 100 gigabit. And then down there, LR4, pretty straightforward, very long. It's a 10 kilometer solution and a LAN WDM, so the spacing between the wavelengths inside our transceiver is 5 nanometer spacing, similar like at 100 gigabit with the 5 nanometer spacing there. Okay, finally, when we come to the physics, we got even more plugs now for 400 gigabit. So you might be familiar with the MPO one. I'm not a fan of MPO because it's damn difficult to produce it and also to get it maintained in the field out there. And it can be a hassle because you get 8 lanes in total and they have to connect, each of them have to connect very precisely. There will be a new one called MPO 16, yeah, hooray. 16 fibers in total. The great thing is it has a new keying, so you can't mix it up. So you can't plug in an MPO 16 into an MPO 12 receptacle from your 100 gigabit SR4, for example. Not possible. And especially on the single mode side, dual LC for sure will be there, and a new one called CS plug. It's basically half the size of a LC plug, just squeezed it together. You could also call it LC double density. I just have seen a couple of days ago a new application getting rid of the MPOs, especially about MPO 16 or MPO 12. When it comes to this type of application, I have to go back to that one, because currently you have here an MPO plug, you have to plug it in. And if one connection is making trouble or the plug is making trouble, you have to unplug it entirely, so all the other 3 links will drop down. There will be a new plug coming out, and I have seen the first samples. It's called the SN connector. I don't have a picture yet, but it's pretty much a kind of an MPO plug, but you can take it apart in 4 parts in totally. So the great thing is you can plug all 8 fibers entirely in there, but if you want, you can take out 2 only and not the entire plug. That's pretty unique, and I hope I can show some pictures in the near future. Finally, power consumption, that's a really critical one. When we had heard about the talk about Huawei at the beginning, yes, there is more and more power consumed, but just think about the figures. So the first, so the OSFP is rated up to 15 watts, and 15 watts doesn't sound much, but if you have a 1U switch having 32 ports of 400 gigabit, you might end up with, just for the optical pluggables, with 500 watts. And not taking in consideration that we got power supplies, that there is a CPU still in there, some ASICs, some memory. So this will end up with a 1U system, 1U rack unit, 400 gigabit, 32 ports, running at 1 kilowatt. So now you have to feed in 1 kilowatt, great, but you have to get rid of those 1 kilowatt in terms of heat dissipation. And that's one big lesson learned made for the OSFP and also for the QSFP-DD, that the manufacturers agreed, okay, we have to increase the amount of power we can put or can feed into such a transceiver, because we have seen issues with the 100 gigabit QSFP-28, for example, because not all kind of technologies were able to build in there. And when I'm talking about what kind of technologies are interesting is when we are thinking about beyond 30, 40 kilometers up to 80 kilometers, thinking about coherent DWDM running on a single lambda 400 gigabit or even 100 gigabit, it doesn't matter. It's really a tough job to get that into a QSFP-28 form factor, which is only allowed to have up to 6 or 7 watts. So these lessons were learned for OSFP and QSFP-DD to increase that amount of power which you can feed into that transceiver. So we will see, but currently at the current stage they are not available, but looking down in that glass bowl down the road for the next 2 or 3 years, we might see coherent DWDM solutions for OSFP and QSFP-DD. And the overall power consumption, the QSFP-DD is currently a little bit behind the OSFP, and that's also what I see on the roadmap when we are looking at which transceivers will be first on the market. That's going to be the OSFP, and I'm pretty sure by the end of the year, early beginning next year, we will see the first 400 gigabit switches with OSFP coming out from Arista. I have seen already one of them, and let's see by Christmas where we are at with those 2 form factors. Right. This also brings me almost to the end about the pluggables. It's still important for us to take care about the compatibility when it comes to the programming. Why do I mention that? Still in the 100 gig, we have seen issues when the first 25 or 30 kilometers QSFP-28 ER4s were introduced. They were not recognized or didn't work at all in the legacy layer 2, layer 3 gear. So we changed the configuration of that transceiver to be a LR4 that the host was able to operate it and light up the laser. So that's what we have done, for example, in the 100 gig. And I'm pretty sure there will be some tweaks to do for 400 gig as well. That's it from my side. Thank you very much for listening. And if you have questions, I'm happy to take them. We should do a coffee break now.
Yeah, just one more lecture. Okay, thank you very much on behalf of the organizers.
Great, thank you very much, Nadia.
Thank you.